What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we are going to be doing part 2 of our breadth first search traversal of binary trees. Today's problem is slightly harder than last week's problem, so if you haven't seen that one, I highly suggest you go back and look at that where we go over the basics of this algorithm. If not, keep watching. Let's solve a problem. All right, binary trees, level order traversal, otherwise known as breadth first traversal. Let's go over quickly what that is, a little reminder for us all. Binary trees are data structures in which a node is linked to two successor nodes. Often we're asked to traverse the tree, meaning look at the nodes making up the tree in a specific order depending on the type of traversal. We're focusing on level order traversal or breadth first traversal for this little mini series. For this interview pattern, we will be exploring breadth first traversal, aka level order traversal, which is when the traversal is level by level in the tree. And to do this, we will use the queue data structure. Again, this should all be familiar from last week's video. If not, go back and check that out. Do some little review before we move on. So let's just, walk through using a tree what level order traversal would look like. Here we have a binary tree with the nodes 1, 2, 3, 4, 5, 6, and 7. So the first level will be the level 1, which has the only node it has is the 1 node. Level 2 has the 2 and 3 node. So we would do the traversal 1, 2, and 3 before we ever got to 4 or 5, 6, or 7. And then finally, we'd traverse that third level, which is made up of 4, 5, 6, and 7. So this is as opposed to depth first traversal, where you might go down an entire branch of a tree, maybe 1, 2, and 4, before you got to the other nodes of the level that you were originally looking at. So what's this week's problem? Given a binary tree, connect each node with its level order successor. The last node of each level should point to a null node. So what does that mean? So here we have our tree, 1, 2, 3, 4, 5, 6, and 7. And this problem is saying that each node is not only going to have a left and right associated with it. So one's left is 2 and its right is 3. It's also going to have a .next property. If it's the last node of the level, its .next will be null. And if it's not, it should point to its level order successor, aka its other next sibling in the level. So 2.next will be pointed to 3, 3 is last, so it will be pointed to null. 4.next will be 5, 5.next will be 6, 6.next will be 7, and 7.next will be null. So it's only slightly different from last week's problem. And you can imagine that as you're traversing, you basically do a level order traversal, editing each node's .next unless it's the last node in the tree. The last node in the level. So, this is a slightly harder problem than last week, but again, it's more or less going to use the same algorithm and the same scaffolding. So what is our approach here? So first, we're going to, of course, initialize a queue and push the root onto it. This is key. You have to know when you're doing a breadth first search that you need to use the data structure queue, which is first in, first out, similar to if you're standing in line at the grocery store. While there are nodes in the queue, we are going to capture the level size. And again, this is exactly the same as last week. It will be the queue.length with each iteration of our while loop. We are going to initialize previous node, and we're going to set it equal to null at first. And then we're going to do a for loop of size, level size. And this is essentially what we'll do in that for loop iteration. If there is a previous node, set its .next to the current node. So if we've already seen a node and previous node is not null, remember previous node will be null only at the beginning of the level. So if there is a previous node, set its .next to the current node, set the new previous node to be the current node, again, moving previous node just along in the level. And then we're going to push our left child and our right child onto the queue to be looked at a further later iteration of our outer while loop. So this will work because we are never going to have our last node in our level we're never going to have it point to anything else. Its .next will never point to anything else, because by the time we get to that last node in the level, we are going to have exhausted our for loop, because we're only doing a for loop for the level size. So our last iteration of the for loop, our current node will be equal to the last node in the level. And so it will just have its .next equal to null, and then we will restart our while loop, where we'll be on our next level, previous node will be null, and we will start again. So pretty straightforward. Let's watch a little visualization of this approach. So here's our tree with our nodes, 1, 2, 3, 4, 5, and 6, and 7. We have our queue with our root pushed onto it to start. We have our level size, which is 1. Previous node we initialize to null, and we shift off of our queue. So we grab that 1, our current node is 1. It's just the one iteration of our for loop, because level size was 1. We can set our previous node equal to 1, but it doesn't matter. It's the only iteration of our for loop. And we move on to pushing 1's left child and right child onto the queue. So let's watch that happen. We push dot left to the queue, we push 2, we push dot right to the queue, we get 3, and we call it a day. We go back to the top of our while loop. Our level size is now 2, previous node gets reset to null, and we shift off of our queue. We take that 2, that's our new current node, and this is the new node we're looking at. Previous node is null, so we don't do anything, but we do set our new previous node equal to our current node. So now our previous node is 2, and we iterate again in our for loop. So now but first we have to push 2's children, so 2 dot left and 2 dot right, that will be 4 and 5 onto our queue. So we've just pushed 4, we push 5. Now we iterate again in our for loop, we shift 3 off of the queue, our new current node is 3, and we do have a previous. So now we're going to set our previous node 2 dot next equal to our current node 3. There's our arrow that signifies dot next. And then we're going to push its left and right children to the queue. So we also set previous node now equal to our current node. We want to keep moving that along. So previous node is now 3, and then we push 6 to the queue, and we push 7 to the queue, and we're done with our for loop. So now we're at the top of our while loop again. Our level size is 4 because we have 4 things in our queue. Previous node gets reset to null, and we shift off of our queue. So now we have 4. Our new current node is 4. We have no previous node, so we continue, and 4 also has no children, so there's nothing to push to the queue. We also set our previous node equal to our current node, which is 4, and we iterate again. We shift 5 off of our queue. 5 is our new current node, and we do have a previous node. So now we set our 4 dot next equal to our current node, which is 5. There we go, and we move on. Previous node is now 5. Shift off of the queue. Now we have 6 as our current node. We have a previous node, so we set 5 dot next equal to 6. There's our arrow, and we move along. And first we set previous node equal to 6, which is our current node, and then we continue. Okay, so we shift our last node off the queue, 7. We have a previous node, so we set its dot next equal to 7, and we finish our entire iteration, right? There's nothing left in the queue. So let's talk about our time complexity and space complexity, our big O here. So our time complexity in this algorithm is a big O of n. And why is that? Where n is the number of nodes in the tree. So why is that? That's because we will only ever loop as many times as there are nodes in the tree. Our biggest loop is going to be our for loops for each, which will only ever go to n, where n is the size of how many nodes there are in a given level. We're going to do that for every single level. So that's how we get a time complexity with a big O of n, where n is the number of nodes in the tree. Because despite the fact that we have a nested loop, we have a while loop, and inside of that is our for loop, our while loop is actually just keeping track of the levels, and the for loop is just going through the nodes in each level. So there's never going to be any exponential nested looping that we loop through something for every element of something else or something like that. I hope that is kind of clear and makes sense. And what's our space complexity? Our space complexity is also a big O of n, where n is the number of nodes in the tree. Because the only thing that's actually growing that we're keeping track of is going to be our queue. And at most, we will have n, where n is the number of nodes in the tree, elements in that queue. So that's how we get a space complexity of a big O of n. Let's code this problem out. Okay, so I'm in Visual Studio Code with a totally blank file, and to start with, we are going to define our node class. So let's call this tree node. Let's say class tree node, and let's say that gets a constructor, and let's say we pass in a val, and we can set the node's val to be what we pass in. We can set its left equal to null, its right equal to null. And then what's different about this problem for this week versus last problem last week is that each of our nodes is also going to have a next property. Let's say that this dot next is also equal to null to start. And let's define our tree, which will be the same test case that I was using in the slides. I'm just gonna do that really quick. So let's say we have a new tree node, and this is going to be our 1, and then we're going to say our root.left is a new tree node, that's gonna be 2, and then its right is going to be 3, and then let's do that last level. So our left.left is going to be a new tree node 4. Our left.right is going to be a new tree node 5. And then our right.left is going to be 6. And then our right.right is going to be 7. Okay. And then I think I'm just going to define a function here, and I'm going to call it connect level order siblings. And that's not, there we go. And this is going to take a root. Okay, so I think we're all set up to start coding this problem out. We have our tree, we have our tree nodes, and we have our function. So first, like usual, we are going to define our queue. So we're going to say our const queue is an array, and we're going to initialize it with our root in our queue as our first kind of order of business here. And then we are going to do our while loop, and we're going to say while the queue has length, iterate, and then we are going to just kind of capture a few things. So at this point in our iteration, we have the queue dot length is going to equal our level size, right? So, and this is going to be the start of the level. So let's say our const level size is going to be queue dot length. And then we are going to also initialize our previous node. So this is going to be let previous node equal to null. And I'm using let here because we are going to be updating that previous node to be, to move it along the level as we iterate through the level. And we want to do this before we do our for loop, which will be here. Let's do that right now. I is equal to 0. I is less than the level size. I plus plus. And the reason why we initialize our previous node up here is because we want to reset our previous node for every new level. So this is kind of our opportunity to reset that previous node for every time we begin traversing a new level. Okay, so we have our for loop, and we are now looping over the entire level. So what are some of the things we want to do? We want to grab our current node, off the beginning of the queue. We want to, if previous node exists, which it only will when it's not the first node in the level, we want to set its dot next equal to the current node. We want to move previous node along. So previous node is now going to equal our current node. And then we want to push children onto queue. That's all we really want to do here. So let's start this. So first we're going to grab our current node off of the queue. So we're going to say const current node equals queue.shift, and we are shifting because we want to take off the beginning because this is the queue, first in, first out. If previous node exists, so if previous node, we're going to set its dot next equal to the current node. And remember, again, I'll say this 10 times, if we don't have a previous node, that means we're at the beginning of the level. If we have a previous node, we can just set it to the current node, and that will be the blue lines from the slides where we connect all of the level order siblings. We will move our previous node along. So we'll say our previous node is now equal to our current node, so that the next time we iterate through in our for loop, so let's say we finish this and we're back up here, we will have a previous node and we will set its dot next equal to the next current node. And then finally, that comment belongs up there. Finally, we're going to push children onto the queue. So we're going to say if current node dot left queue dot push current node dot left, and then if current node dot right, we are going to push current node dot right. And that's it. Can you believe it? So it's really only slightly different from last week's. So that's the whole algorithm though. And the way you really can know that this is how, the reason why you can do this so easily if you've mastered this pattern is because you are so used to initializing a queue, doing this while loop, iterating over the levels with the nodes in each level with this for loop, and knowing when to initialize this previous node, when to reset it to null, and when you have the opportunity to set the last previous node's dot next to the current node that you're looking at in the level traversal. So those are the pieces that you really want to know, like down pat, so like well in your mind, so that if you get a problem like this, you know the small tweaks you can make to actually write the algorithm and solve the problem. So I think the last thing that we're going to do together is write a custom print method on our tree node class, which will print our level roots, are the root nodes of each level, and all of the nodes that it points to, et cetera, So we see that 1 points to null, 2 points to 3 points to null, 4 points to 5 points to 6 points to 7 points to null. So let's say that we are going to add this to our tree node. Let's call it print. And then down here at the bottom, we can just say like so root.print. So we're basically going to call print on root. And so at this point, we are going to have a this, and this is going to be the tree node we've called print on. So we're going to start by setting our level root. We're going to say let our level root equal to this. So our first root that we're looking at, our first level root, is going to be the node that we call this on. And then we are going to initialize the while loop, and we're going to say while there's a level root, do all this stuff. And you'll see when there will and won't be a level root and when we will be iterating here. We're also going to initialize a current, and we're going to set that equal to the level root to start. And here is our first console log statement, where we are going to say level root, and then we're going to say level root val. So basically at this point, we are at the start of the level. Okay, so that's our first console log statement. We're at the start of the level. We have our level root. What do we do now? So at this point, what we want to do is we actually want to reset level root to be null. And the reason why we want to do this is because we already want to be, we want to set our level root to be the next level's root while we print out the rest of the level, because we'll have access to, if you can imagine, the level root, the next level's root will be the previous level's root dot left or dot right if it doesn't have a dot left. So this is our opportunity to kind of push our outer while loop along so that the next time we iterate, the level root is then the next level's root. If you're not following, hopefully at the end of my writing this, it will become clear. So we have a level root of equal to null now, and then we're going to initialize an additional while loop, and we're going to say while there's a current. So this while loop is iterating over the levels. This while loop is iterating over the nodes in a given level. So I hope that's clear to everybody. So we have while there is a current. So now we are going to be going through our current level. So the first thing we're going to do is we're going to say if level root is equal to null, which basically means we're at the beginning of the level because we just reset level root to null. We are going to take that opportunity to capture our next level root. Remember, because we only have one opportunity to capture the next level's root, and that's when we're looking at a level root and we can get its dot left or dot right if it doesn't have a dot left, because that will necessarily become the next level's root. So if level root is null, we're at the top of the level essentially. We want to say if current dot left, we are going to set level root equal to current dot left. If it doesn't have a left, else if current dot right, we are going to set the new level root equal to the current dot right. So that's our opportunity to set our level root, our next level root. Okay, so now we're in our while loop, and we want to iterate in this while loop until we've looked at all of the nodes in that level, and we've printed each one and what it points to. So at this point, we can have our next console log statement, and we can say, remember, the first thing we printed was level root, whatever, and now we can say points to, and we can say that it points to, does current have a next? If it does, print current.next.val. And the reason why I'm using this double ampersand is because if current doesn't have a next, this would error out because we'd be checking it for a value of something that doesn't exist. So we get to our level root, let's say 1. It doesn't have, we're in this second while loop. Level root is null because we've reset it to null. 1 does have a left, it's 2, so we set level root equal to 2. Current is now also equal to, current is equal to 1 at this point, so it points to nothing, right? It just points to null. And then we move on. There is no next current. So the last thing we have to do here is move current along, right? So now current is going to equal current.next. So when we're iterating over the 1, current.next is equal to null. So our new current is null. We've finished that level. We go back to the top. There is a level root because we set it here. Our next level root will be current, the old current, which was 1. So now it will be its dot left, which will be 2. And we will continue. So we will say level root 2, and then we will have a new current, which will be 2. Level root will be null because we've reset it. It has a left. 2's left is 4. So our new level root will be 4. And here we could say points to, right? The last thing we wrote was level root 2 points to, and current.next, it does have a .next. next? It's 3. So we'll say that points to 3, right? And then current is now going to be current.next, which is 3. So we'll loop back around in this inner while loop, and we'll say we have a current, we have a level root, so don't reset it. Just say points to, and then current.next, this will be null. So 3 will point to null, which it's supposed to, and then current will be null. We'll exhaust this inner while loop. We'll go back to the start of our outer while loop for our third level and continue. So let's see if that actually does what we wanted it to. So let's say node code. Okay, so it's not what we wanted it. So it says level root 1 points to null. That's what we wanted. Level root, oh, I know why, because we didn't actually call our connect function. So none of them are connected. So that makes sense, right? They're all just pointed to null. We have our 3 level roots, 1, 2, and 4. They all point to null. So let's actually call this function connect level order siblings. So let's say connect level order siblings, pass in that root, and now let's see what we get. And it looks like we have an endless loop. So why is that? Okay, so we have 2 and we have 2 pointing at 3, so that's what we want here. Oh, so I think it's because we want these things to be out of this if, right? We want to move current along even when level root is not null, not only when it's null. So let's see if that fixes it. Yes, it does. Okay, so we have level root 1 points to null. That's what we want. Level root 2 points to 3, which points to null. That's what we want. Level root 4 points to 5, points to 6, points to 7, points to null. So that's what we want. So I think this is actually a little trickier than the actual algorithm itself for connecting the level order siblings. Understanding why we have these nested while loops and how we're actually iterating over the levels to kind of have this unique print that is perfect for this algorithm and this algorithm only. So I suggest you go over all of this, go over it with a pen and paper, a debugger as usual, and kind of watch how these variables change and why this works. But I thought that would be a fun little extra, something to work on your muscles while your breadth first search muscles, and be more comfortable traversing the tree in different ways to basically have different effects. That's all I got for you today, everybody. It's kind of a rainy day here, so I was excited that I had nothing else to do outside or anything like that. So I thought I'll film a video for everybody. I hope you enjoyed. Join us next week. We're going to be doing a hard breadth first traversal problem. And yeah, I hope you're enjoying all of these in-read patterns. I hope you're enjoying traversing trees. And I'll see you in the next one. Keep up the good work. Bye, everybody.